Launched in 1977, NASA's Voyager spacecraft, Voyager 1 and Voyager 2, stand as two of the most extraordinary achievements in the history of space exploration. More than 4 decades later, they are still functioning and transmitting data from the most distant regions of space ever reached by human-made machines. Voyager 1 in particular has earned the distinction of being the farthest human-made object from Earth, now traveling through interstellar space. The mere fact that a spacecraft built with technology from the 1970s, decades before the internet and smartphones, continues to function and send back valuable scientific information is a testament to both engineering ingenuity and the relentless pursuit of knowledge. The origins of the Voyager mission are rooted in a unique cosmic opportunity. In the late 1960s, Gary Flandreau, a young aerospace engineer working at NASA's Jet Propulsion Laboratory, JPL, made a remarkable discovery while analyzing planetary motions. He realized that the outer planets, Jupiter, Saturn, Uranus, and Neptune, would align in such a way during the late 1970s and early 1980s that a spacecraft launched from Earth could use each planet's gravity to accelerate toward the next, effectively slingshotting its way across the solar system. This gravitational assist technique would cut travel time drastically and conserve fuel. Such an alignment happens only once every 176 years, and missing it would have meant waiting over a century for another chance. Recognizing the rare opportunity, NASA fast-tracked development of the Voyager program. Two identical spacecraft, Voyager 1 and Voyager 2, were constructed to take advantage of the alignment. They were launched just 15 days apart, Voyager 2 on August 20, 1977, and Voyager 1 on September 5, 1977. Despite being launched second, Voyager 1 followed a faster trajectory and overtook its sibling on the way to Jupiter and Saturn. Initially, their primary mission was to study these two gas giants and their moons, but their performance exceeded expectations so dramatically that their mission was extended, ultimately making Voyager 2 the first, and so far only, spacecraft to visit Uranus in 1986 and Neptune in 1989. During their journey, the Voyagers returned some of the most breathtaking and scientifically valuable data ever recorded. At Jupiter, Voyager 1 revealed active volcanoes erupting on the moon Io, the first such volcanic activity observed beyond Earth. Voyager 2 uncovered the complex cloud structures and storm systems of Jupiter, as well as a wealth of previously unknown moons. At Saturn, both probes examined the iconic rings and discovered subtle features like braids and gaps within them. Titan, Saturn's largest moon, was found to have a dense atmosphere, raising the possibility of complex organic chemistry and prebiotic conditions. The extension of Voyager 2's mission to Uranus and Neptune was equally fruitful. At Uranus, the spacecraft discovered 10 new moons and observed a magnetic field strangely tilted and offset from the planet's center. Neptune proved to be surprisingly dynamic, with Voyager 2 capturing images of massive storms, including the Great Dark Spot, similar in scale to Jupiter's Great Red Spot. The spacecraft also discovered Neptune's faint rings and 6 new moons, revealing a system far more active than previously believed. What makes the ongoing success of these spacecraft so astonishing is the technology on board. Each Voyager probe is roughly the size of a small car, yet they carry just 69 kilobytes of onboard memory, less than the storage capacity of a single low-resolution photo on a modern smartphone. Data collected by the instruments is recorded on an 8-track tape recorder before being transmitted back to Earth through a 23-watt transmitter, comparable in power to a refrigerator light bulb. The signals, weak and faint, take more than 18 hours to reach Earth, and NASA's Deep Space Network must parse them from the background noise of the universe and human-generated radio interference. To maintain contact, the Voyagers rely on 12-meter-wide, high-gain antennas and communicate via light-speed radio waves. As they move farther from Earth, now at a rate of 3 to 4 light seconds per day, NASA engineers have had to continually refine techniques to pick up their increasingly faint transmissions. Updates and course corrections, which were sent from Earth long after the launch, have required precise calculations and a deep understanding of both orbital mechanics and the aging limitations of the spacecraft's hardware. Eventually, both Voyagers crossed a crucial threshold, the heliopause, where the pressure of the solar wind is balanced by the interstellar medium. This invisible boundary represents the outer edge of the Sun's influence, a region where particles and magnetic fields from the rest of the galaxy begin to dominate. Voyager 1 entered this region in 2012, followed by Voyager 2 in 2018, officially, marking humanity's first presence in interstellar space. Their instruments have since provided the first direct measurements of this uncharted realm, revealing variations in cosmic rays, magnetic fields, and particle densities that are reshaping scientists' understanding of the galaxy's structure and the protective bubble formed by our sun. As the Voyagers move toward the distant and still hypothetical Oort cloud, a vast shell of icy bodies thought to encircle the solar system, they continue to serve as emissaries of Earth. Each spacecraft carries the Golden Record, a gold-plated copper disc containing sounds and images representing the diversity of life and culture on Earth. Compiled under the direction of Carl Sagan and his team, the record includes greetings in 55 languages, music from various cultures, and eras including Bach, Beethoven, and Chuck Berry, and recordings of natural sounds such as thunder, waves, and birdsong. The hope is that if intelligent extraterrestrial life ever finds one of these spacecraft, they will have a glimpse into who we are and what we value. Despite their remarkable longevity, the Voyager's days are numbered. Their power sources, radioisotope, thermoelectric generators, RTGs, are slowly running down. These devices convert heat from the decay of radioactive material into electricity, but the amount of power they produce diminishes with time. NASA engineers have already turned off non-essential systems to conserve energy, and by the mid-2030s, both spacecraft will likely lose the ability to communicate. When that time comes, they will become silent travelers through the galaxy, moving at nearly 17 kilometers per second, bound for the stars but no longer in touch with their makers, yet their legacy will endure. The Voyager mission has revolutionized planetary science, inspired generations of engineers and scientists, and deepened humanity's understanding of its place in the cosmos. These two aging probes, launched with the technology of the 1970s, have traveled farther than anything else ever built by humans. They have demonstrated that with vision, precision, and perseverance, even the most ambitious goals in science and exploration are within reach. The story of the Voyager missions is one of courage, curiosity, and the unyielding human desire to explore the unknown. These tiny spacecraft, launched more than 4 decades ago, continue to teach us about the universe and remind us of how far human ingenuity can reach. As they drift silently through the stars, they carry with them the voice of humanity, a message in a bottle cast into the cosmic ocean. If stories like this inspire you as much as they inspire us, don't forget to hit the like button, subscribe to the channel, and turn on notifications so you never miss a journey through space and science that challenges what we think is possible. Let's explore the universe together, one discovery at a time.